ain't going to the town without go back to work. I gotta buy my kid a brand new pair of shoes. I'll drink a little bit that evening, sing a little bit of these working man blues.
All right, welcome back. This is Mr. McMurray singing the Working Man Blues here on Tuesday morning. All right, and we are going to do some momentum. All right, so momentum change is greater when bouncing occurs. Wow, that's a neat idea. Let's talk about that one for just a second. Let me pause for a second and let it set up here. All right, now let me see if I can get this set up correctly. I was trying to do this a minute ago and it wasn't really cooperating with me. We may have to do it small screen. I don't know if we can go large screen. There we go. Okay, just have to do it while we're going. All right, as you can see here, I have 2 blocks of wood. I have identical looking little black balls here. Okay, and they have identical blocks right here. All right. And what we're going to do is we're going to lift these a certain distance and let both of them hit. Oh, and look at that. This one knocked over and that one did not. And yet they're almost identical balls. Okay? In fact, if we weighed this one might actually weigh a little bit less than that one. Okay? I think I did that. But it knocked this one over and this one did not. The question is why? Well, one small hint. If I drop this one, it bounces. If I drop this one, it does not bounce. So even though they are the almost exactly the same mass, in fact, if anything, the one that didn't knock it over is a little bit heavier, it does not bounce, and this one does, okay? And yet the lighter one knocked over the block, and the other one did not. All right, hang on to that thought, and we will be back over in our regular spot. All right, so here we go. What does that mean? Why does that happen? Well, let's discuss it here a little bit. All right, first of all, I'm going to get me a pen and draw something here. All right, so if I have a pen, let's say I have a wall right here. And I have two balls. Here's the one, and here's another. Okay, this one hits the wall and stops. Okay, let's say it was going 5 meters per second. All right, but it stops. It plops, just like that ball that doesn't bounce. It just hits there and boom, stops. Now I have another ball that's also moving 5 meters per second. Okay, but it bounces off and comes off at probably be a little less than 5, but we're just going to say 5 meters per second. It bounces and comes back at the same speed in the opposite direction. Okay, now, since it's going in the opposite direction, we're going to make it a negative number. All right. Now, momentum change, if these two balls have the same mass, just like the two balls that we had over there, they have about the same mass, then the only thing that can change their momentum is the change in their velocity. Okay. This one went to 5 to 0. It hit the wall and splatted. Okay. This one hit the wall and went from 5 to 0. But then it went from 0, when it bounced, it went from 0 back up to 5 meters per second in the opposite direction. Okay, so this one had a change of 5 meters per second, negative 5 meters per second. Okay, you take the final velocity minus the initial, 0 minus 5, it's going to give you a negative 5. It slowed down by 5 meters per second. Now here, if you take the final one, negative 5 minus 5, you get negative 10. So it slowed down 5 meters per second, and then basically went in reverse 5 meters per second the opposite direction. So it had twice as much of a velocity change. Okay, that's in terms of change in momentum. Now, if we think about it in terms of impulse, which we know causes momentum change, okay, when this hits the wall, it exerts a force on the wall, and the wall exerts a force on it. So it has a certain amount of force, X amount of force. Okay, but here, it hits the wall, and the wall hits it. Then it pushes off the wall, and the wall pushes back when it bounces. And so you have a double dose, if you will, of force. Okay, and so you have twice as much impulse, which is why you have twice as much velocity change, okay? And so when something bounces off, it's going to have twice as much momentum change, and therefore twice as much impulse, and so on, okay? All right, so let me get back up here, and so there's always a greater impulse involved in objects that bounce, okay? Because when an object's momentum changes to 0 and then accelerates in the opposite direction, you're going to have a greater impulse, okay, or you have a greater velocity change, okay? And the shorter time these changes in velocity occur, the less time it takes, the more bouncy the object is, then the greater the force involved, okay? And since you have more force, then you're also going to have a greater impulse, and so that's how that's going to work, okay? So you have greater momentum change, one, because there's a bigger change in velocity, and it's caused by a double application of force. When it hits the wall, it hits the wall and the wall hits back, but also when it pushes off the wall and bounces, it pushes off the wall and the wall pushes back again. And so there's a double amount of force as well. And then if it happens, the more bouncy it is, it happens in a smaller amount of time, then there's even a greater force involved. And that's why something that's very bouncy bounces off harder. Why? And farther than one that's not very bouncy. Why? Because there's a greater force involved there. All right, let me see what else we have. Okay, so a ball bouncing off the wall. We talked about that kind of example, and there we go. All right, so what else do we have? Well, let's talk about momentum being conserved. That's the important thing we're going to talk about today. In order to change momentum, we said you had to exert a net force for a certain period of time, which is the net impulse. Okay? If there's nothing else acting on it other than your impulse, nothing else, no other things affecting it besides them hitting each other or hitting an object being hit, then the total momentum of the system, we say the system just means whatever we're talking about here, the total amount of momentum is conserved, which just means it doesn't change. You can't just lose momentum that just disappears and is not there anymore, okay? The momentum is still there, okay? It can't be lost. And this is called the law of conservation of momentum. Fancy that. Well, every once in a while we label something logically and makes sense, and it just, I don't know how it happens, it just happens now and then. All right. Now, let's talk about a bug on a windshield, for example. Now, you're zipping around the down the road in your car. Okay, I'm just gonna. Okay, that's pretty bad. But anyhow, okay, let's just say a truck. We always use a truck, but we could use a car if you wanted to. Anyhow. All right, this is your car. And this is our little buggy guy up here, okay? When you hit the bug, first of all, which one exerts more force on each other? It is the same, okay? And which one exerts the force for a longer time? Well, the same. The truck hits the bug just as long as the bug hits the windshield, okay? So the force is the same, the time is the same. That means the impulse is the same, which is force times time. And that means the change in momentum is the same, okay? And so the change in momentum is exactly the same. Therefore, the amount of momentum for the whole system is the same because the truck is going to slow down slightly, okay? But the bug is going to speed up a whole bunch in reverse directions, go the same direction the truck's going. So basically, in this case, the amount of momentum is going to be the same. Beforehand, you had a big mass of the truck, and it was going at a pretty big velocity. Okay? In the opposite direction, you had the little mass of the bug and a little velocity of the bug, not going very fast. Okay? Now, to find the net momentum, well, this velocity is positive. This velocity is going the opposite direction, so we call it negative. All right? So it'd be this big number times this big number minus this little number, okay? Because it's going to be a negative number, but it's going to be a tiny number, so it's going to be almost the same as the truck's momentum. Well, after it hits the bug, the new momentum of the bug, let me see here, is going to be, it's going to be a big mass, sorry, it's still going to be a little tiny mass, sorry, my fault. But now it's going to have about as big a velocity as the truck because it's going to be going at about the same speed the truck is in the other direction. Okay? And the truck is going to still have a big mass and it's going to have about the same velocity. Okay? Now, technically, the truck's velocity is going to be a little bit smaller. My drawing skills have gone bad. Let me find my thing here. Okay. So it still has a big mass, and its velocity is a little bit smaller, but so small you can't hardly tell the difference. Well, this is a tiny mass times a big change in velocity. but this one has a little bit less velocity. When you add them together, you're still going to end up with the same total momentum that you had before, okay? So keep in mind, the total momentum is what's going to be the same. The change in momentum is identical for the bug in this, but the speed of the truck hardly changes at all. The speed of the bug changes a whole bunch, but it's time a small amount here. So it's going to be just a little bit less momentum, because now they're both going the same direction, but they're not going quite as fast as the truck as it was before. And so the momentum is still the same. Okay? Hopefully that wasn't more confusing than helpful, but we'll see. All right, now another way to look at it, let's look at a cannon. All right, before you fire off the cannon, the motion of the cannon is 0. So the momentum, which is mass times velocity, right? Mass times velocity is 0. Okay, yes, you got a big mass of the cannon, you got a mass of the cannonball inside here, but it's mass times velocity. And if the velocity is 0, then the whole momentum is 0. Now, when we fired the cannon, okay, the cannon shoots backwards. So now it has a big mass. Whoops, let me try that again. Big mass with a relatively small velocity. Okay, but it's going this direction. So we would say it's a negative velocity. All right, now the cannonball has a much smaller mass. Okay, but since you have the same force acting on it as on the cannon, you're going to have a big velocity. Okay, and it's going in the right, so we're going to call it a positive velocity. All right, someone says, well, now we've got two momentums. Before we had momentum of 0. That can't be right. Okay, because here the cannon and the cannonball's momentum was 0 up here. How can we have two momentums that be right? Well, this one is a negative momentum. All right. Let's just say it's negative 40. I don't know what units it is. Guess what? The ball over here, it has a smaller mass, but it has a faster velocity, and its momentum will also be 40. But it's a positive 40, and so we would say the net momentum, we'd find the difference between the two, and we would find it's still 0. Okay? So keep in mind that just because the momentum is conserved, it doesn't mean that they stay the same. Okay, they can change, obviously, in this case, quite a bit, and still be a conserved or momentum of 0. All right, momentum in collisions. Oops, I went off the top there, but that's Roman numeral 6, momentum in collisions. Momentum is always conserved in collision when two objects hit. Okay, like the other one was an explosion, I guess, when the cannon goes off. This would be a collision when two objects hit each other. Okay, so the net momentum before the collision is going to equal the net momentum after the collision. All right. Now, in elastic collisions is when objects collide and are not permanently deformed and do not generate heat. In other words, they bounce. They change shape when they hit, maybe, but boom, they bounce off. They don't generate heat. That is considered an elastic collision. Okay, an example would be of a golf ball. If you hit a golf ball, it actually flattens the golf ball on the side. Okay, it flattens the golf ball on this side over here. It deforms it temporarily, but after it hits it, it goes back and is not permanently deformed. Now, does it generate some heat? Yes, it's going to also generate heat. So just for the record, there are no perfectly elastic collisions in the real world except for on the atomic level. Okay, but that would be elastic because it bounces off. Okay, all balls that we hit, tennis balls, golf balls, etc., are going to be elastic collisions. Okay. In the everyday world, there are no perfectly elastic collisions. If you run your car into someone else, you're not going to just bounce off perfectly. It just doesn't work out that way. Okay, and so most collisions we say are more elastic or less elastic or inelastic if they're not elastic at all. Okay, and so in fact, most collisions in the real world are going to be somewhere between elastic and we'll talk about in a minute inelastic. All right, but there are no perfect ones. The only example of perfect elastic collision where things bounce off is on the molecular level. If you have atoms, so for example here we have this atom sliming into this one and they bounce apart, that would be a perfectly elastic collision. And we are going to have to finish this up in another video. Short one though. See you back in a little bit.